Alright, so everyone, today let's start this final lecture we have in this course on wireless communication, and I wouldn't like to cover anything very heavy or significant today. I'm just going to briefly recap and wrap up with the concept of Doppler effect in wireless communication systems. So we've gone through several aspects of wireless communications. I hope I've been able to give you some flavor of the challenges and the theory and analysis of these different aspects of wireless communications and wireless communication systems. Uh, and for the last couple of lectures, we've been characterizing the wireless channel, right? And we talked about several properties of several aspects to characterize the wireless channel. We said one of the main aspects of wireless channel, one of the key defining properties of a wireless channel is the delay spread, right? What distinguishes a wireless channel from a normal digital communication system or from a normal conventional communication channel is that in a wireless communication system you have multi-path propagation. So naturally that means you have multiple components that are arriving over a delay, hence you have a delay spread. Therefore you have a delay spread, and you have a delay spread, and also we said there are different metrics to characterize this delay spread. One is the maximum delay spread, tau max. The other is the RMS delay spread, tau RMS. So this is the maximum delay spread, and this is the RMS. This is the RMS delay spread, tau. And of course, tau RMS we said is a much better metric because it helps you characterize the delay spread in a very practical and sort of a very sort of much more practical compared to the maximum delay spread. And also we saw these delay spreads typically, both the RMS and these delay spreads are of the order of microseconds, typically 1 to 3 microseconds in delay spreads are typically 1 to 3 microseconds in outdoor channels. That's what we said in this thing, that is typically 1 to 3 microseconds in outdoor channels. Uh, and the other thing that we said, we looked at several examples to characterize the delay spread, and the other important aspect or the other important parameter we defined for the wireless channel is this. This is the coherence bandwidth. If you will remember, what we said is the coherence bandwidth is basically, if I take a wireless communication system and look at the bandwidth of the channel, that is, if I look at this is my channel filter, if this is my magnitude response of the channel, if this is magnitude of h of s, then this part, this is BC, is the coherence bandwidth. This is the coherence bandwidth of the channel. What is the coherence bandwidth of the channel? To put it simply, coherence bandwidth is basically the frequency range over which the channel response is flat. Further we said, if the signal bandwidth, if BS, basically BS is the signal bandwidth. If the signal bandwidth is less than the coherence bandwidth. If the signal bandwidth is less than the coherence bandwidth, then what kind of a channel is this? Can someone tell me what kind of a channel is this? If the signal bandwidth is less than the coherence bandwidth, then what kind of a channel is this? Can someone tell me what kind of a channel is this? Can someone respond via chat? If the BS is less than, if the signal bandwidth BS is less than the coherence bandwidth BC, what kind of a channel is this? What do we call such a channel? Can any student respond? If BS is less than BC, what kind of a channel is this? Yesterday we talked about some terminology for this channel, and of course if BS is less than greater than BC, yes, that is correct. If BS is less than BC, then this is known as a flat fading channel. And if BS is greater than BC, this is a frequency selective channel because the distortion this is known as a frequency selective fading channel. That is, if BS is greater than BC, this is known as a frequency selective channel. Correct. There is BS less than BC, BS greater than BC. One of them is flat fading, one of them is frequency. Of course, if BF is greater than BC, then we say there is distortion in the received spectrum. There is distortion in the received signal spectrum. And also we saw that in the time domain, we saw interestingly that this also has implementation in the time domain. In the time domain, also we said that the relation between coherence bandwidth and delay spread is TD equals 1 over 2 BC or BC equals 1 over 2 TD, because we said that the coherence bandwidth is inversely proportional to the delay spread, that is coherence bandwidth BC is inversely proportional to the delay spread. As the delay spread increases, the coherence bandwidth decreases. That is, for a small delay spread, the coherence bandwidth is large, and for a large delay spread, the coherence bandwidth is small. Right? That's what we said. And also we said if you look at it in the time domain, if the delay spread TD is greater than or equal to half the symbol time, then we have intersymbol interference. That is correct. If the delay spread TD is greater than or equal to Ts by 2, then we have inter symbol interference. And of course we also said if TD is greater than or equal to Ts by 2, TD is equal to 1 over 2 BC. And what is Ts by 2? Ts by 2 is 1 over 2 Bs, that is signal bandwidth. So it says 1 over BAC, 2 BC greater than or equal to 1 over 2 BS, which means Bs is greater than or equal to BC. That is, we get the same condition for frequency selective. Is everyone able to follow this argument? What you are saying is, if there is intersymbol interference, it corresponds to basically the same condition as frequency selective fading. So frequency selective fading basically implies intersymbol interference in the time domain. So there are two ways to look at it. One is the time domain, other is the frequency domain. The time domain is basically intersymbol interference. The frequency domain is frequency selective fading of the wireless communication system. So there is time domain and then there is frequency domain with frequency selective fading. Alright, so these are some of the different aspects. This looks at the delay spread, comprehensively summarizes the delay spread aspect of the wireless communication system, and it is a key parameter because of the delay spread. If there is a fixed delay spread, which means your symbol time cannot exceed the delay spread, and therefore which means your symbol time cannot be much smaller than the delay spread, therefore you are limited by a certain maximum rate that can be transmitted on the wireless channel. For instance, let me give you this example. If the delay spread, let's calculate this simple thing. If TD equals let's say 2 microsecond, what is maximum symbol rate for the wireless channel? Can someone tell me this? If TD equals 2 microseconds, what is the maximum symbol rate for the wireless channel? Can someone tell me what is the maximum symbol rate for the wireless channel? Yeah, symbol time. What is the maximum symbol rate? The maximum symbol time, I think everyone is confused. The maximum symbol time is 4 microseconds, right? Because if you look at this, TD has to be greater than or equal to TS by 2, right? To avoid intersymbol interference, TD has to be greater than or equal to TS by 2. I mean, for intersymbol interference, TD has to be greater than or equal to TS by 2. To avoid intersymbol interference, TD has to be less than or equal to TS by 2. So TS has to be greater than or equal to 2 TD. So TS has to be greater than or equal to 2 TD equals 4 microsecond. Now if TS is equal to 4 microsecond, if TS is equal to 4 microsecond, what is the signal bandwidth? Bandwidth of the signal, or what is the rate of the signal? Final signal rate or bandwidth is one and the same thing. What is the bandwidth of the signal? If TS is equal to 4 microseconds, what is the bandwidth of the signal? What is the bandwidth of the signal? If TS is equal to 4 microseconds, what is BS? What is the bandwidth of the signal? That is correct. Bandwidth of the signal equals 1 over 4 microseconds, that is 10 to the power of 6 divided by 4 equals 250 kilohertz, right? So 250 kilohertz, and what this says is bandwidth of the signal is 250 kilohertz, implies rate, maximum rate equals 250 kilo symbols per second, right? So what this is saying is very interesting. It's saying you have a maximum signal bandwidth of 250 kilohertz, and therefore, and this is similar to, by the way, this is similar to what we calculated for the coherence bandwidth, no surprises there. And therefore what this is saying is 250 kilo symbols per second is the maximum rate at which you can transmit over the wireless channel, right? Because if you make the symbol timing smaller, then you will have intersymbol interference. To transmit at a higher rate, you have to decrease the symbol time. So what this is saying is that the maximum symbol rate that is possible is 250 kilo symbols per second. Everyone, makes sense to everyone? The maximum rate is 250 kilo symbols per second, because if you transmit at a rate greater than that, then you have to decrease the symbol time, and if you decrease the symbol time, then there is going to be symbol interference. I hope that logic or that logical argument is clear to everyone. That is why we are limited by a maximum rate because of the delay spread, because delay spread causes inter-symbol interference if the symbol time is made too small. That is the problem. All right, and so that is basically the idea. And there is so one of the key aspects, because delay spread, and several people had asked me initially, how does delay spread affect wireless communication? This is basically how it affects wireless communication, because delay spread actually limits the rate of a wireless communication system, which means if you want to transmit at higher and higher rates, you have to come up with novel and innovative schemes. And in fact, there are several such schemes. For instance, OFDM is one such scheme. Unfortunately, we could not cover it in this course because of lack of time. I feel because of lack of time. Anyway, we'll try to see if we can cover that in a later course next time. So the other thing that I want to move on today is basically talk a little bit about the Doppler spread, something that we haven't talked about so far. So the next thing that I want to talk about is basically briefly, and with which I will wrap up my discussion today. The Doppler effect is another significant aspect of wireless communication system. Can someone tell me anything about a little bit about the Doppler effect? How does the Doppler effect? I mean, what is the Doppler effect? How does it affect? What is the definition of the Doppler effect? Can someone tell me? Yes, correct. Because the user is mobile. So because the user is mobile, what is happening because of the user is mobile? Yeah, because the user is mobile, there is an apparent change. The Doppler effect is nothing but the change in the carrier frequency. Because of motion, in fact relative motion between user, actually it has to be transmitter and receiver, but we are talking about a mobile communication scenario, so it is the user and base station. For instance, I have tried to demonstrate this schematically over here. For instance, if I have a velocity v, which is I have a user who is moving with velocity v, sorry, I could not get this. Let me redraw this again. So let's say this is a mobile station, this is a base station, and user is moving with velocity v, but the angle is theta, that is the angle between the signal propagation and velocity is theta. Then the Doppler frequency, Doppler shift is given as Fd is v cosine theta by c, where c is the speed of light, times Fc, where Fc is the carrier frequency. So Doppler shift is v, where v is the velocity, theta, cosine theta, where theta is the angle the velocity makes with the line joining the mobile station and base station. C is the speed of light. Fc equals Fc is the carrier. Fc is the carrier frequency. So what this says is there is a shift in the carrier frequency. What is that shift? That shift is proportional to the velocity v angle theta. And see, now you can see if the velocity is high, the Doppler shift is high. Of course, if theta is 0, that is the user is moving directly along this line joining mobile station and base station, Doppler shift is high. But if the user is moving perpendicular, then the Doppler shift is 0. And c is the speed of light. And of course, the carrier frequency itself has an important role to play, right? Because if the carrier frequency is large, then the shift is also large. If the carrier frequency is small, then the shift is also small. So the shift is proportional to the carrier frequency. Therefore, I have v equals v cosine theta by c into fc. Let's take a simple example. Let's take a simple example to evaluate this. Let's say V is equal to 70 kilometers per hour. V is equal to 70 kilometers per hour. Theta is equal to 0. That is, the user is moving directly along the direction of directly towards the base station. And FC, the carrier frequency, is let's say 1.85 gigahertz. Let's say the carrier frequency is 1.85 gigahertz. Can someone tell me what is the Doppler shift? Can we calculate the Doppler shift? So all colleges, my question is this. I've given you a formula. This is actually very straightforward. I have given you a formula that is FD equals V cosine theta divided by C times FC. That is, there is a Doppler shift FD, which is V cosine theta by C times FC. I've said that V is equal to 70 kilometers per hour. Theta is equal to 0 degrees. That is, the user is moving directly towards the base station. FC, the carrier frequency is 1.85 gigahertz. Can someone tell me what is FD, the Doppler shift? Can we calculate this? All students, so this is a question to all the students. Can we calculate what is the value of this Doppler shift? And let me just write down probably a part of the solution also. So we have 70 kilometers per hour. 70 kilometers per hour is basically 70 uh, let's take a look at 70 kilometers per hour is 70 into 5 by 18 meters per second into cosine theta is 0. Theta is 0, so cosine theta is 1. So 1 divided by 3 into 10 to the power of 8, which is the velocity of light, into the carrier frequency, which is 1.85 into 10 to the power of 9. 1.85 into 10 to the power of 9. Can someone calculate this value? Can everyone? Okay, I have one answer, that is 120 hertz. Can someone else calculate this and try to see if this is correct? Okay, very good. So it looks like everyone is saying it is 120 hertz, so it's approximately, let's write it approximately 120. So that is the typical value of the Doppler. It's around 50 to 100 hertz. 50 to 100, of course, here the velocity and carrier frequency are both high. Typically the value of the Doppler shift is around about 50 to 150 hertz. So typical value of Doppler shift and for vehicular velocity, typical values of Doppler shift are around 50 to 100 hertz. Now, what is the impact of this Doppler? What is the impact of this Doppler shift? That is something that we have to understand. Uh, for instance, see, remember we had our baseband channel. To that, understand that. Let us go back to our baseband channel model. I hope everyone remembers the baseband channel. Baseband channel model. I hope everyone remembers the baseband channel model. Now, remember, we said our baseband channel model is basically given as h of e equals summation ai delta, well, this is not the baseband channel, this is the passband channel. So if I write the base, well, let me write the passband channel. This is tau minus tau I. Therefore, baseband model, the baseband HBT I equals 0 to L minus 1 AI e to the power of minus j 2 pi fc tau I. We said this is the baseband channel. In fact, we said this is the baseband channel coefficient, right? So this is the channel coefficient. This is, by the way, h of tau. This is the channel. So what we said is, if everyone remember, that the wireless channel is a sum of different multipath components, each coming with a different attenuation AI, different delay. So this is the attenuation, this is the delay, and therefore in the baseband equivalent channel model, the attenuation is the delay basically turns into a phase factor, right? This is the phase factor. So I have the baseband channel coefficient. In fact, we said this is the baseband channel coefficient. This whole part, we said this is the baseband channel coefficient, right? This whole part, this is AI e to the power of minus j 2 pi fc tau I is the baseband channel coefficient. Now let's take a simple example. Let's say this is my base station, this is my mobile station, and mobile station is moving with a velocity v at direction theta, and the delay is tau, right? The delay is tau. The delay along this path is tau. So this is my mobile station, this is my base station. BS means base station, MS means mobile station, and my delay is tau, right? The propagation delay is tau. Now if the mobile is moving with velocity v at an angle theta, what do you think is going to happen to this delay? I'm not looking for an exact answer, but can someone tell me what is going to happen? I mean, can we have a qualitative answer that if, let's say, the propagation delay, this is tau, the propagation delay is tau, the delay will vary, correct? How will the delay vary? What can someone give me an idea? That is correct, the answer is correct. The delay will vary. Can someone tell me, give me an idea of how the delay will vary? If the propagation delay is tau, how will the delay vary? Delay will vary as a function of time. Very good. Can someone give me a better, well, it might be slightly difficult. So let's look at this. Let's go back to our undergraduate physics. What we can do is we can decompose this velocity as two components, velocity perpendicular and velocity parallel to the direction. In fact, the velocity perpendicular will have no effect on the distance, because the distance along this direction does not affect the propagation distance. It is the velocity that is parallel to the direction that will have an effect. Therefore, the velocity along the direction is v cosine theta. Velocity along the direction to the base station is v cosine theta. And hence, after a time t, what will happen is this distance will decrease by v cosine theta times t, which means the propagation delay will decrease by v cosine theta by t by c. So my propagation delay tau of t is tau minus v cosine theta t by c. Can everyone see this? Does this make sense to everyone? See, what I'm saying is the following thing. Please understand this thing. This initial delay is tau. Initial delay is based on this propagation distance, right? Initial delay is based on this propagation distance. Now, because the mobile is moving, what is happening is this propagation distance is decreasing. Because the propagation distance is decreasing, the delay is varying. How much is it varying? What is the amount this propagation distance decreasing by? If v is the velocity, theta is the angle, v cosine theta is the velocity in this direction, Therefore, the decrease in distance after time t is v cosine theta t divided by c. V cosine theta t is the decrease in distance. V cosine theta t divided by c is the decrease in the propagation time. Therefore, the net propagation time is the initial propagation time tau minus v cosine theta t by c. And therefore, if I can substitute this, if I can indulge you for one more slide, if I can substitute this, I have hbt equals summation ai e to the power of minus j 2 pi fc tau I. Now this tau i's will become functions of time, because the propagation, because we said the delays are varying, therefore the tau i's are functions of time. And in fact, I can substitute for this I equals 0 to L minus 1 ai e to the power of minus j 2 pi fc tau I minus v cosine theta t divided by c. We said the delay is decreasing, tau I is decreasing by v cosine theta t divided by c, which means I have I equals 0 to L minus 1 ai e to the power of minus j 2 pi fc tau I into e to the power of j 2 pi fc v cosine theta by c into d. But look at this, fc cosine theta, fcv cosine theta by c. What is fcv cosine theta by c? Can someone tell me what is fcv cosine theta by c? We just defined it. We just defined it. What is fcv cosine theta by c? That is the Doppler frequency fd. That is correct. That is exactly correct. So therefore, this is equal to, what is this equal to? This is equal to summation I equals 0 to L minus 1 ai e to the power of minus j 2 pi fc tau I e to the power of j 2 pi fd t, right, where fd is the Doppler frequency, right? And now you can see, previously this was the phase, now you see this is the phase factor which is time varying. Look at this. This depends on time. This is the phase factor varying with time. As a result, the whole channel is time varying. Therefore, the phase factor is varying with time. Therefore, whole channel becomes Therefore, the whole channel becomes a time varying channel, because the phase factor is varying with time. The whole channel becomes a time varying channel, because the phase factor is varying with time. The whole channel, the channel itself is where the whole channel itself is becoming a this channel itself is becoming a time varying channel. So what is the effect of Doppler shift? What is the effect of Doppler shift? The effect of Doppler shift reduces time variation in the wireless channel. Doppler shift introduces Is this clear to everyone? Doppler shift introduces time variation in and how fast or slow is the variation? If the Doppler shift is high, is the variation high or is the variation low? Can someone tell me if the Doppler shift is, if FD is high, what can we say about the variation, the rate of variation? If the Doppler shift is high, What can we say about the rate of the variation? If the Doppler shift is high, what about the rate of variation? Is the variation high or is the variation low? If the Doppler shift is high, the rate of variation is high. The variation is changing faster and faster, right? If the Doppler shift is high, the variation is fast. Everyone can see that, because if the Doppler shift FD is 0, that is V is 0. If V is 0, then there is no change, because FD is 0, then this is always 1. It is only if you have a high Doppler shift FD that as the frequency is high, the variation is high. The Doppler shift, as the Doppler shift is high, if FD is high, the variation is high. And therefore, that is correct. The coherence time, now I want to define something known as the coherence time. The coherence time is the amount of time the channel is constant or static. The approximate amount of time, again this is a rule of thumb. Approximate time for which channel is static is coherence time, Tc. And if Fd is high, if the Doppler shift Fd is high, is the coherence time high or low? If the Doppler shift coherence time is the time for which the channel is static, that is the time for which the channel is not changing. If the Doppler shift is high, therefore the coherence time is low, right? If D is high, Tc is low. Therefore, Tc is inversely proportional to 1 over Fd. In fact, a rule of thumb, again if I have to give a rule of thumb here, Tc equals 1 by 4 Fd. So Tc equals 1 by 4 Fd. This is the coherence time. Fd is the Doppler shift. Fd is the Doppler shift. Okay, so Tc is the coherence time, Fd is the Doppler shift. Can you tell me, for instance, we calculated Fd value previously, we said Fd is equal to 120 Hertz. What is the coherence time Tc? Tc is equal to, can someone tell me what is the coherence time Tc? What is the coherence time Tc? Is Fd equal to Tc equal to Fd is equal to, can someone calculate this value? What is the coherence time? Tc is equal to 1 by 4 times 120 equals 1 by 480, approximately equals 2 millisecond. Correct. If we approximate 480 by 500, this is approximately 2 milliseconds, 2.08 milliseconds. Very good, very good. So coherence time is approximately of the order of milliseconds, right? So that is the thing. So what we are saying is the channel is time varying. Because of the Doppler shift, the channel is time varying. And coherence time is 2 coherence time here is 2 milliseconds. What we are saying is coherence time is approximately of the order of milliseconds. That is, The channel is changing from millisecond to millisecond. So within 1 second, the channel is changing roughly about 1,000 times, right? So this channel has to be measured and some other things. So this has implications, like these are key parameters of a wireless communication channel. What does channel variation mean? Channel variation means that the channel has to be measured or estimated at the receiver. So these are the processes that have been carried out at the receiver in the wireless communication system. All right. So I'm not going to go too much into the details of this beyond this thing. My main aim was to introduce the Doppler shift, the Doppler effect, and the Doppler nature of the wireless channel, which arises because of the mobility, because if the user is mobile. What this is saying is there is mobility, so naturally that means the delays are changing, therefore the channel is changing. Now what is the rate at which the channel is changing? The channel is changing at the Doppler frequency FD. The channel is changing with the Doppler frequency FD. So if FD is faster, if FD is higher, the rate of variation is higher. And the coherence time, the amount of time for which the channel is static, is inversely proportional to Doppler frequency. In fact, TC equals 1 by 4 FD. We saw for the case of our example of I think 70 kilometers per hour, 1.85 gigahertz. This Doppler shift is 120 hertz, which means the coherence time is 2 milliseconds. Therefore, the coherence time is approximately 2 milliseconds. There is a question: what is fast and slow fading? The question is well, it's complicated to define what is fast and slow fading. It depends on the application. If the channel variation is faster compared to what the application demands, or if the channel variation is faster then the rate at which the channel can be estimated, then it is fast fading. And if it's not, if it is not that fast, if the user velocity is very slow so that the channel is constant for a strong period of time, then it is a slow fading channel. Right? So if the mobile moves away from the CS, I think that is also obvious because we said V cosine theta. If you move away, then the angle theta will be greater than 90 degrees. Therefore, cosine theta will be negative. Cosine theta is negative. The Doppler shift is automatically negative. In this case, if the user is moving away from the mobile, you can see theta is greater than 90 degrees. Therefore, cosine theta is less than 0. Therefore, naturally the Doppler shift is going to be negative. Yeah, makes sense. Yeah. All right, so I think here let's keep this lecture today light. I think just because this is the last lecture, I think I just want to wrap up with Doppler shift without starting anything new. Of course, this is a course on wireless communications. We have only covered a fraction of wireless communications. In fact, this is the basics of wireless communication, and this is where, in fact, the concept of wireless communication in fact begins, and then you cover different wireless technologies such as CDMA, OFDM, MIMO, etc., and so on, and different other technologies. Unfortunately, we could not do a lot of that in this course, as I've already mentioned, because the amount of time is very small. Because over 15 to 16 lectures, we have to first fill the background. However, what we have done, and let me again emphasize what we have built on, we have built a strong grasp of, or I have tried to build a strong base of the fundamentals. What are the fundamentals? The fundamentals of a wireless communication system are basically the aspect of fading. What is the meaning of fading? How does fading occur in a wireless communication system? It occurs because of the random multipath components. Therefore, it can be well approximated or well represented by a random fading coefficient. What is the nature of this random fading coefficient? We looked at a Rayleigh fading coefficient. And what is the impact of fading? How does fading affect the bit error rate in a wireless communication system? And what is the technique to combat the bit error rate? Or what is, what are the different techniques to combat the bit error rate? And fading, one of the most powerful ideas, that is fading, not fading, diversity. Diversity, for instance, we looked at antenna diversity, where you have multiple receive antennas, right? And we analyzed in detail what is the bit error rate. And then we looked at one of the most important aspects of a wireless communication system, which is the diversity order. And then we looked at some of the key parameters of the wireless communication system, that is basically the delay spread, and we looked at the Doppler shift, and we said, and of course in the diversity order we said that if the diversity order is L, then the bit error rate decreases as 1 over SNR to the power of L. Then we looked at the delay spread, Doppler shift, etc., and so on. And so we built, the way I look at it, we built a a strong base with respect to the fundamentals of wireless communication. I mean, these are the fundamentals that help you understand different aspects of any wireless technology, be it CDMA, be it MIMO, or be it OFDM, because once, if you don't have a grasp of the fundamentals, that is what is the meaning of fading, what is its impact on bit error rate, what is the meaning of diversity, it makes it very difficult to understand other aspects of wireless communication, like what is the impact of an OFDM communication system, what is the impact of a MIMO communication system, etc. So my hope and my aim is I've been able to convey some of these fundamentals. Of course, sitting here hundreds of kilometers away in IIT Kanpur and trying to convey something is slightly more difficult than if I were sitting I were at your institute and delivering this lecture. But of course, I'm fully appreciative of this effort because it's helping me reach a much wider audience. And of course, I'm really heartened by the enthusiasm. I'm really amazed, surprised, and also very happy at the enthusiasm shown by so many students coming at 8 o'clock in the morning. Because of course, several students, I think the colleges are not are in the city, like not in an IIT. In IIT, of course, the lecture begins at 8 o'clock. But I think in several cities, because the college is away from the homes, right? Because students have to travel from the city to the college. So I think the classes start slightly late. Of course, in IIT, everyone, we stay close to our institute. So for us, coming at 8 o'clock is not a big deal. But keeping that in mind, I'm very appreciative, and I'm happy that so many students and so many colleges have participated in this course. I hope I have been able to deliver the lectures in a manner that is understood by students. I have tried to decrease the complexity of the students, considering that this class is being taken mostly by undergraduate students, not postgraduate students, as I normally teach these courses at IIT. So I've tried to make this course content and the pace also suitable for what is a typical undergraduate curriculum in colleges across the country. My main aim is the following thing. My main aim is to basically excite the students, interest the students, and arouse your interest, or basically motivate you to basically pursue a career in wireless communication systems or research in wireless communication systems. Of course, it's a very exciting field. We know all of that. Wireless communications is probably today the field with the highest growth. That is everything that is, I mean, if you look at technology, the forefront of technology, wireless communications is the field which is basically which basically has the highest growth and which is actually attracting everyone from the technology sector. So my hope is that I've been able to motivate you, and my main aim is to motivate brilliant young students like you towards a PhD program in wireless communications, of course at IIT Kanpur and several other IITs also. We have good PhD programs. So think about higher studies, dear students. If you think about higher studies, there is a lot of challenge in this career. There are a lot of exciting opportunities. In IITs, we have a lot of openings for good PhD students, students who want to pursue wireless communication systems, who want to pursue research in wireless communication. There is a tremendous opportunity. There is a tremendous research opportunity. There is a tremendous opportunity in terms of pursuing research and pursuing higher education. What I mean is higher education. When I say higher education, it means masters, and also with a very specific emphasis on the PhD. So I would like all of you students, all of you brilliant students, I'm very excited. So several of you are responding very well to the questions, and it's very exciting and it's very heartwarming to see that. And I hope I've been able to deliver something to you, something of value to you, because of course everyone is putting in the effort to come in at 8 o'clock. I hope the lectures have been meaningful. Of course, all these lectures are recorded, and if you have any question later also, just write me a mail. My email address is available on my website. Just feel free to write me a mail. With this, I think I would like to, of course there are still some questions, there are many questions. Of course, the number of questions, there will be many questions. There's not, definitely there are going to be many questions, not just one or two questions. So I'll take them separately. Can you send me an email? I will make sure that I will respond to that email. Thank you very much. Thank you everyone who have responded positively. And if some feel that this course has not been able to meet their needs, I am sorry. I have to say again, apologize, because I am limited by the time. One is the time, which is only 15 to 16 lectures, and also the medium, which is basically because it's not a live course, so I cannot get basically sometimes there might be questions, but I'm not able to respond to them properly because I'm not able to interact with you in real time. So I apologize for that. I hope this has been a valuable experience. For me, it has been a very exciting experience to reach out to students across the country. And as I said, my main aim is to excite brilliant students like you. And also, I would like to mention that IITs, we also admit undergraduate students directly from the BTech for the PhD program, and this is a very exciting research opportunity available for BTech students. Please keep that in mind. It's not that the PhD program is only for students with an MTech degree. Students who have a BTech degree, and in fact brilliant and motivated students, can also apply for the PhD program, or PhD admissions have already started. So keep this in mind. Do apply for a PhD program. There is a very exciting and a very valuable and very profitable career in research and development in wireless communications awaiting all of you. Thank you very much. At this note, I would like to end it. My thanks to all the teachers who are participating. My thanks to all the students who are participating. My thanks to the QEEE program which has made this happen, which has helped me reach a wide audience. Thank you very much. I totally enjoyed teaching this course. I hope you have enjoyed this too. And keep it in mind that there is a career in research that can be pursued by young and brilliant students like you. This course does not have to end here. There is a vast open area for research that is awaiting all of you to keep it in mind. Thank you very much. Thank you everyone. I would like to end this course on this note. Thank you all.